Hi and welcome to another Hopper on microcontrollers video. This one's on the Raspberry Pi Pico, and it's the subject matter is hosting other languages on the Hopper virtual machine. In other words, I've got this idea of being able to write other interpreters and possibly other compilers in Hopper, so write the language in Hopper and target the Hopper bytecodes in the Hopper virtual machine. So what I've done here, this is the basic language that I had running on the 6502 in the same way. It's based on Gordon Henderson's GIBL, which is based on something called nibble. There's a link to Gordon's work in the description below. It gave me some discipline to try to support the specifications from a third party, like Gordon's basic exactly. So let me just launch this in the debugger. There we are. And just get on with it. So if I just run it right now, let's just do that, F5. It's loading. There we go. And it's if you look down on the screen below, you can see we've got the titles come up. Tigger Basic, GIBL variant running on the Hopper BEM. So I could do things like 10 for I equals 1 to 10, 20 print I, 30 next I, and then run that. There we go. So we basically got some basic. Clear the screen. I've made it run all the samples that Gordon has with his project without changing the syntax at all. So this one, for example, is Noel's Retro Labs benchmark for basic. It's designed for small machines, but it runs anywhere. So this is how long it took to tokenize, and this is how long it took to run on 16-bit integers, for example. And yes, I have it hooked up to a TFT LCD right now. There's another video I've got on drivers for these for multiple different microcontrollers and different screens. Let me back out of this. So exit that. Back in the debugger. Exit the debugger. I'm going to disable the screen so that I can get well, I don't need to, but that's how quickly I can disable the screen. So use LCD. Down in the bottom of the program here, this is the main. This is Hopper's equivalent of a main. It doesn't say main. It's just an anonymous method in your program. And use LCD. All it was doing was initializing a display. That's pretty much it. And then elsewhere, it just knows there's an LCD available. Might as well use it. So if we rebuild now for notice without the display, so we just build. Bottom of the screen, you can see it's building. So this display will stay the same. So what I could do actually is just unplug it so that it goes blank, so it's not distracting. Oh, I could just switch off the screen, I guess. I could do that too. Yes. Let's just do that. Okay. So we're now just going to run in the serial console. So if I launch the debugger again, this is a good way to demo as well. Another one, I translated the Byte magazine benchmark from the 80s into GIBL, Gordon's basic dialect, tiny basic dialect. So this is I'm pasting it in with the clipboard into the serial port to the device. This is the basic Civ benchmark, prime benchmark from 1980 from Byte magazine. So it's kind of interesting to see this. So it takes 5.8 seconds. And the reason it takes 5.8 seconds is because it's running in the debugger. So I could put breakpoints in here, and put a breakpoint on there. So in the debugger, it took 5.8 seconds. if I start without debugging and paste it in again and run it again, it only takes 1 second. So the debug is quite a big overhead. You can also turn brake checking on and off. So play on words on tron and trough is broth and bron and broth for turning brake on and off to check for brake guys. It's a bit of a performance hit if you got a poll for Control C being hit all the time. Anyway, I'll do one more demo, and that is I can also launch from here without the debugger, just directly with Control F5. So from the editor I can go launch with or without the debugger. So Control F5 would be launch without the debugger, and that's kind of a nice place to go and use Gordon's Mandelbrot example. There we go, 3 seconds to do the Mandelbrot, not bad. I know, another nice example, but let's turn the LCD on again. So go back there, do that, build it again for the LCD, and switch in that LCD. Okay, it's successfully compiled this at the bottom of the screen. So now I'll run it full screen here again, but I've got the LCD running. So Control F5 should blank out that LCD there. Yep, it's cleared the screen. And then this is one of Gordon's, I don't think it's his, but it's in GIBL. He definitely modified it. Prime example. So we run this prime number example, and it says what's the upper limit of primes we've got to look for. I'll go 1200. And it finds us some primes. I did that because I know that 1200 fits on the LCD, obviously. Anyway, that's about it. It's a pretty neat little dialect of Tiny Basic. You can see, if you look in the links below here, you go and have a look at Gordon's project and you can learn a bit more about it. And the purpose of my exercise was to use it as an example of, so this here is about a 5,000 line project in Hopper to re-implement Gordon's Basic, and then to generate code. So if I look for instruction here, so this is generating, these are Hopper virtual machine bytecodes that it's generating, and so we could do this with any language. So we could implement other interpreters, like Forth, for example, or we could implement other compilers. Hop is a compiled language, so other compilers like Pascal or C we could do this way. So you end up with a full, this is running on Windows, this IDE, the IDE is written in Hopper, the debugger is written in Hopper. So we could have, and the whole tool chain for compiling, compilation process is also written in Hopper, and so it's a full symbolic debugger running on Windows that's connected to your Raspberry Pi Pico via a serial port. And I like the performance of these of this basic is just about as good as if I wrote this in Hopper directly, simply because it's running on the same bytecodes. It's a little bit more verbose. In fact, I have an example. I've got my Notepad++ here. Let's have a look. So, where is it? Yeah, Noel's RetroLab example, this one. So this is Noel's RetroLab example. So we can see the code in here. This is what the basic looks like. And then when it's converted into Hopper bytecodes, it looks like this. So this print S instruction is translated into these 7 bytecodes. So push immediate this value, which is actually the variable S, because it's reading a word from memory, which is that variable's location. It's an integer, so it's converting it to a string. Now it's got a string on the stack. It's a stack-based virtual machine. Then it calls print to print it. Anyway, so if we went and looked at how it's kind of neat having these calls, because it means I don't have to write the more complicated functionality for the language, like printing things. I don't have to write that in assembly. I can write it, let's do that to full screen. I can write it in Hopper directly. So the way that works is if it's calling something like this error, for example, or you know, it's like it hit a division by zero here when it was doing the division, so it checked for 0 and then it called this error pointer, and that's in what I call platform, and that's where I write Hopper library functions, helper methods written in Hopper to be called from the VM bytecode, so you don't have to write everything in assembly. So where was that one? Error pointer here. It's this thing error. So what does it do? What does error do? So let's find its definition. Yeah. So it gets the current line number. So that's, and at runtime, we're talking about inlined Hopper virtual machine code. So it's got to keep track of what the line numbers are for each, for where it is in the instructions, which it does. And then it'll call this error method, which prints out a nice pretty error message with what error it was. So it'll have a description of the error and the line number. So this division by 0 error, for example, will let's go have a look what the errors look like. So errors. So somewhere in here there'll be a division by 0. Here we go. It'll say division by 0 and the line number, for example. So I didn't have to write all this in assembler. I could just use my helper functions, which will be, so you can have a runtime library basically that's written in Hopper for whatever language you're writing. So if we write a Pascal compiler, we could have a runtime library. The runtime library for Hopper is actually, for GIBL is actually very small. That's all the functions. That's it. And I use the Hopper delegate feature. The Hopper language has delegates which are like C function pointers, but they're a bit safer to use because they're type safe. C++ type safe as well, but they're a good feature. Anyway, I think that's a good place to end this one. Let's just put that Mandelbrot back up again. Why not? So let's launch that again. So this is running without the debugger. Just pasting in the code for Gordon's Mandelbrot example again and running it. And yeah, it doesn't fit on the LCD, but I'll show the LCD anyway. So it wraps a bit because this LCD with this font doesn't have enough room for it. Anyway, thank you for watching. I look forward to your comments. This is all on my public repo as well, latest source code.